Day 12. And we're definitely getting into the computer science zone now. We've got some pathfinding to do. So essentially, we've got this grid, and we start at the letter A, which is where the S is. So under the S is an A. And we need to navigate this grid. And we can step up one letter. So we can go from A to B, but we can't go from A to C, for example, or any higher than that. And our job is to navigate this grid so that we step on letters either one above or the same or lower than the letter we're currently on, and to find the shortest path through to the destination E, which will be Z. And we're supposed to be trying to get to kind of high signal. So you can see this kind of come through here. We go through, this way, I guess, and this way. This way? Is that right? Oh, no, it's not. This way, this way, this way. All the way around, all the way around, and then all the way around again, and all the way around again, and all the way around. Yeah, so you get the idea. This is the puzzle input. It's pretty big. I don't know if it's square or not. It might not be. But it doesn't really matter. There are two differences to the way I approach this to the previous ones. The first one is that I have done most of the planning already previous to this video, because the planning was getting quite long, and I don't think that interesting to watch me stare at the screen and try and figure out what on earth was going on, at least not until I can get a bit sharper with the planning step in terms of how I'm cognitively managing it, because there's a lot of just kind of fuzziness in that. And I've also written a utility library, just to kind of reprise some of the work from yesterday, and double down on the technique that I was mentioning before. And I think I'll probably only do that when I fail the day. I'll probably only work on the utility library when I fail the day, or when I've got extra time left over, because I don't want to spend loads of time on this. Got better things to do with my life than just get sucked into aven of code. So yeah, anyway. So it's pathfinding, and if you've done this exercise, or you've any idea what it involves, I've either made the mistake already, or I'm onto the right track, and only you'll know. I'm going to use the A-star routing algorithm, or the pathfinding algorithm, which is a kind of, I guess, well, it's reasonably well known as a pathfinding algorithm across things like this. It relies on a heuristic, and essentially the way it works is, let's actually look at the Wikipedia page for this algorithm. You can hopefully see this example here, which illustrates how it works. It tries to go directly there, and if it can't, it sort of tries increasingly divergent paths around, and then it goes kind of around until it finds the right, so it gets to the path and then tracks the path back from the end to the start. And it doesn't rely on it being a grid, it just relies on it being a graph. And we can imagine this graph as, if it was a grid, we could imagine each graph as it does here, sort of up, down, diagonal, etc. But for us, the graph's not going to be up, down, diagonal exactly. One is going to be only up, down, left, and right, but it's also not going to be able to go up a jump in slope. So we're just not going to treat those cells as connected. So that gives us, a beginning to our approach, and I've manually executed with a mistake right at the beginning here that I hopefully didn't impact anything. I've manually executed the A-star algorithm with this toy example. Essentially, the way it's worked is I've gone here to here, and then to here, and then to here, and then to here, and then we end up with a dead end here, and then we go all the way around and spiral into our goal. This is like a subset of the trial, and there are a few things we need to keep track of. The goal, the current cell we're on. We'll need to calculate the neighbors of the cell we're on, which will require some custom logic. We need to go through each neighbors. We need to generate something called a G score, which I think is the actual score, and an F score, which is the estimated score. We need some kind of slightly fancy data structures to do this. We need a dictionary with an infinite default, and we might need something called a priority queue or a heap queue or something, but I'm hoping we won't. If we run out of time, if it ends up taking too long though, then we might, but we'll see. I've then sort of made some notes on the way I want to structure the program. So building on the work from yesterday, we're going to need a state thing. We're going to definitely going to need a cell data structure. I'm not going to implement this at first, but I think we can use the vertical distance as part of the heuristic. But I'm just not 100% sure whether that will cause problems, so I'm not going to do it at first. And we need to essentially write something to pass the grid, something to find the lowest current F score, so the current kind of estimated score. We need to have something to construct the path once we've got all of the sort of calculations done, something to get the neighbors of a cell and not sort of jump 2 steps higher, something to calculate the G-score, and then we can build this sort of main algorithm here. And here's where you'll probably see some of the utilities that I've written come in useful, hopefully, or they'll be more trouble than they're worth. And I've got some notes on the data structures I want to use down here, and all this. So this is going to be, I guess, a little less engaging from the planning step. I'm curious to know if that's useful or not. But I think we've pretty much got everything necessary to start, and a few tabs open as well, just in case we need them. And yeah, I think we can get going. This is going to be tough to write all of this in half an hour, if I'm honest. But we'll see. It's definitely possible. It's just whether I'm going to be able to do it without making any mistakes. And if we run into some efficiency problems at the end, whether I'm going to be able to improvise my way to the right approach, make the right decisions as to which one needs to come first, things like that. I do have a bit of time to run the code after the half an hour and still win the day, so I might try to rely on that if it looks like it's likely. I've also set up my editor in a slightly different way, and I've got type checking working, so that should help a little bit today as well versus yesterday. I've got a meeting in about an hour, so we best get started, especially if I'm going to run over. Okay, we switch to VS Code. There we go, and let's start the timer, and we're good to go. Okay, my plan here. Okay, so first thing I'm going to do is create myself a cell, import data classes, and cell's going to have X, which is going to be an integer, Y is going to be an integer, and Z that's going to be an integer. I'm then going to go and assert a to cell, which if I give it an A at, I guess, 0 and 1, or 0, 0, then I should get, rather use my check function. This should come out to be a cell of, pass these in like this. This should come out to be a cell of 0, 0, let's say 0, 1, and this one should be 1. And then if I import this from my utilities, then this should get the same, but this should be 26. And everything else should go in the middle. So let's drive that. X, Y, char. And then the char is going to be the org, which I think is like this. Cell rather, X, Y, and then the org of the, come on, character minus, what's a lowercase a? Minus 97, so minus 96. Okay. Does this work? Great, it does. Now I'm going to need to have some special cases for start and end, which are going to, this one's going to be 1 and this one's going to be 26. So say if char is S, come on. Okay, and then in this case, Z's going to be 1, in this case, Z's going to be 26. Okay, that still works, great. Okay, now I'm going to pass the grid, and I'm going to need to get my trial out. Actually, I've got to do that. Okay. This I'm going to use my utility library for, what did I call it? Every line. State here, and the file name. This one takes state, file name, and then functions. Okay. Okay. Maybe I should drive the state first. I think I might actually. Let me do this. Okay. State, which is another data class. This is going to be a list of item of cell, sorry. Open set is going to be a list of, yeah, a list of cells. Is it fit? Think of cell to cell. G-score is a dit of cell to int. Score is a dit of cell to int. Goal is a cell. Current is cell. Neighbors is a list of cells. Neighbor is a cell. Tentative G-score is an int. Found path is a list of cells. Okay, great. So I'm going to take a state and a file name and pass it the state. And then I'm going to have a this line Okay. Right, and um, the line is going to be here, and we're going to iterate over each character. I'm going to call chart to cell with the row, which will be the Y rather. Um, so this will be X, this will be Y, X, Y, and then the character itself is going to be this. And then we can say if the char is S, then state goal is current is we keep track of the start as well. Just in case we need it. And then state goal is to sell, and then we can return, we can state grid Y, basically end line to state. Okay, so now if we pass in, put in a state with, am I going to have to put in all these defaults? Yes. That work? No, it doesn't. No default val. Uh, anyway, we get rid of all that. I can't not pass them in, I think. Oh no, wait, I can. Oh, god damn it. Okay. Okay, let me do this properly. Uh, so this is going to be a list, dictionary, dictionary. No, don't do that. grid open set came from dict. Okay, fine. All right. Nothing then? Nothing at all? No, I'm running the wrong file. I'm running the wrong command. Okay, something's wrong here. Did I just forget to save? Is that what that is? Okay, well, I think that works. X, Z1, Z2, Z3, Z13, 13 on the end. Okay, great. Great. Okay, goal. Do we get the goal? Yes. And do we get the start? Yes. Okay, great. So that works. Now, I do need to get this to be a default dict with infinity. Came from is fine. Okay, this one is some default dict. With a lambda, I think. Mm -hmm. Hey, all right. Great. Okay. Wow, we're definitely not going to get this done in the right time. Okay. I'm going to do, yeah, okay. Finalized F score state. Okay. Okay. And actually, what's the minimum index? And that's very dull. It's not going to work, is it? Not at all. No. Okay, let me do this the ugly way. It's less than the lowest. Lowest is okay. I have to do this as well. So to calculate the F score, we get goal is state goal. And we get the cell, and we return okay, goal x minus cell x plus goal y minus cell y. Great, okay. We may as well do G score, we're here. Which is got by the G score of the current cell. Named terribly. So let's say G score of the state, current state of the neighbor. So it's the G score of the current, rather. So let's not get this actually. Plus, essentially in this case, 1, which is always going to be the distance. So we can say that the tentative G score, we can set this. We'll set that later. Okay, so we've done those. Now let's get them with this. Okay, so we're going to say left is the state current left is going to be in the same y and x minus 1. Right is going to be plus 1 if it exists. Up is going to be same x minus 1y, and down is going to be plus 1. Any of these may not exist. Okay, so if this one is less than 0, we can say settle those. Then within this, we can just say neighbors empty, and then and okay, if state current x is greater than the length of state current y, right? And then the same logic applies here. And here, I'm just going to check that run off by 1. 3. So if this will fail, so it needs to be greater than or equal to in these. No, less than or equal to. Less than, strictly less than. Okay, and then we want to filter on, is it this? I'm not typing neighbor this many times. N for N in neighbors if Z is less than the state current Z plus 1 less than or equal to. So 2, 3 less than or equal to 3 plus 1 is fine. 2. No. 4 is fine. 5 is not. Okay, great. Okay, that should get us the neighbors. Now this should be relatively straightforward. Which is we have to go through and construct from, came from, and the goal, a path, which means current is state goal, or while, rather, it's while, isn't it? While current in is it current none is not none. How do you move something onto the start? Fine, you can't. Okay, and we can return reverse. Okay, now, okay, that's time. That's another failure for today. Okay, it's not the same as state goal. State current is find lowest F score with the state. Well, basically, this is going to be true. Current is state goal and return and construct path with the state. Otherwise, state open set. Remove state current. State neighbors equals neighbors state or neighbor path. Neighbors state. Then we want to state came from So it came from the neighbor to the current G-score from the neighbor should be the tentative G-score, and the state F-score should be tentative plus the, the heuristic plus this, essentially. And if the neighbor, if not neighbor in state open set, then open set and all right, and allegedly this works, which it won't, obviously. Let's add some logs in here, I think. Okay. That's on line 82. The open set should start with something, shouldn't it? Yeah, it should begin with the start cell. Yeah, which I should do in here, I think. State open set and cell state G score cell should be 0. State F score cell should be, well, it should be calculate the F score with the start, which I think it will find fine. I think it will manage that. To move these up. Okay, right, it's unhashable, fine. That's it. Okay, and we end up with the set getting empty, which means there's no path. So let's add some more logging here. Zero, zero. Okay, so let's look through this. So we're going from here then to x2, y0, which is too far. So that's wrong. Why the neighbor's wrong? Okay. X, Y, stop this, please. I don't want that there. Okay, whatever. Okay, 0, 0, neighbors are 1, 0, 0, 0, 1. So we're going through the neighbors here, and we can say we can look at this, and then we can have this be here. Okay, so going through this one, we're going through. So the neighbors include itself, which it shouldn't. Don't know how that's happened. Left, right. Oh, And we've got right and down. So right is going x plus 1, which it is. And down is going y plus 1. But y plus 1 is not getting set properly, or the grid is wrong. Let's print the grid. Okay, now what have we got here? This one, yes. This one, okay, y is not getting set properly. Fine. That makes sense, we're getting line 0 multiple times. And that means my utility library is broken, which it is. I don't know if I'm going to assume this is handled efficiently. Okay, so we definitely get further there. This is on line 85. Yeah. Coming from line 126 here. Okay, so where do we end up? What do we end up passing through? This would be a great time to visualize the grid a little bit. Where do we end up at? We end up at 7, 1, 12, which is 7 along, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7. And then 1 down, we end up here at L. Okay, the only next step is to visualize this, I think. Don't think I'm going to get any further with this style of debugging. It's going to be too complex. But we can probably see maybe any early errors if they're visible here. So we should end up going. What about if we just try the really simple version? That we can try and debug it a little better. So does it work with this version? No. Okay, so we end up going, well, okay, so I mean, I know one reason why. It's because this should be, let me just tweak this. So if we say this is going to be 23 instead, you. Okay, so where does this get to? It goes, so we're starting at 2, 2, and then we go to 1, 2. And then we go to 2, 1. And we add both to the open set, which makes sense. Then we step to 2, 2 again for some reason. Did I remember to remove it? Not there, obviously. Then we step to 2, 2, but it shouldn't matter, probably. Then we step to 1, 2. And then we step to 2, 1. And then we don't add any more for some reason. So we're not adding any more, even though there are neighbors here. We're not getting the new neighbors. We're missing some neighbors. So the neighbor for 1, 2, the neighbors for 1, 2 should be left and down. And we're actually just getting, no, the neighbors for 1, 2 are going left and down, which doesn't make any sense. Even this is weird. It's the same cell, we're getting different ones. Okay, let's call this a fail. I've got another meeting to go to, so I'm going to go set up for that, and I'll set going on this later. Okay, I realize I've got a few more minutes. So I just spotted, we got some off by 1 errors here again. So I fixed those, and now we get to a hang, which means that we're getting through to reconstruct path, and reconstruct path is never terminating, which means we may have a cycle here. Or it may just be not moving on. Oh, I know it. I know where it is. Obviously, it's got this totally wrong, don't I? Okay, so current should be state came from, and then yeah, now we get the thing. And this is irritating. So we go, the path should be, well, you get the length of the path. So this path length should be is 7, and I can verify my manual version is 7 indeed. Okay, let's try the full trial. 32, 31. Well, I'm pretty sure that it's probably not counting the final step, right? Let's check the path. So 0 to 0, 1, to 2, 0, to 2, 1, to 2, 2, 2, 3, 2, 4, 3, 4, 4, 4, 5, 4. I think I should go along again. 6, 4, 7, 4. Then up, 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 all the way. Then left, which it does. Then down, which it does. And then right. Wait, x3, y3. Yeah, yeah. Okay. Then x4, 5, 6. Then up again, up again. 5, 2. Yeah. So yeah, I think that is right. It's just one too many. So let's say the steps is -1 steps. Okay. This is the len 31, and we don't want the full path, I think, with the full one. Okay, let's try it with the real one. That's not helpful. I want the grid. 4, 8, 4. Let's try it. That's correct. Okay, so definitely a fail, and there are a couple of minutes in there when I wasn't recording, so we can. I don't have the time at all reflected, but it's 1 p.m. now, and I could probably work out when I started. Maybe anyway, I'll just add like a couple of minutes to it. Okay, so that's food for thought. I mean, the approach worked. It's just there are too many bugs and found too late. Is there a way to? And actually, I didn't even finish coding by the time I'd. Anyway, all right. Part 2. Walk up the hill. Spec the elves want to turn this into a hiking trail. The beginnings are very scenic though. To maximize exercise while hiking, the trail should start as low as possible, elevation A. The goal is still the square marked E, however, the trail should still be direct, taking the fewest steps possible to reach its goal. So you need to find the shortest path from any square at elevation E to the square marked. Wait a minute. I guess that doesn't really matter. Just didn't change that back. Suppose it just stepped down. Yeah, that was the same, right? Yeah, I just noticed that there was a bit of my code that I deliberately broke and didn't change. But anyway, now there are six choices for starting position, five marked A, plus the square marked S that counts as being at elevation A. If you start at the bottom left square, you can reach the goal most quickly. This path reaches the goal in only 29 steps, the fewest possible. What is the fewest steps required to move from starting at any square with the elevation A to the location that should get the best signal out? How many A's do you think there are in this? Brilliant. There are 1,059. So we could just try calculating them all. How long does this take? So that takes half a second. Half a second times 1,000 is 500 seconds, 5 minutes. It's not so bad. Otherwise, we'll need to reuse the tree in some way. Which we could do. We know where they're linked. We should keep a list of all the A's. So in theory, I'm just thinking the F score should still be useful. Wherever we are on the map, the F score is still useful. The G score, the G score is not useful. The F score is calculated from as the estimate from the So the G score won't be useful. The G score won't be useful because it's dependent on the source. All the information that's dependent on the source, on the start, we're not going to be able to work with. At least not without kind of doing some fancy work. So we could loop over, but we're not going to find out whether we're right till the end. That'll be annoying. But we could reverse this and have the highest point be the start and try to locate the shortest path to an A of any kind. We would need to know where, for this routing algorithm, we need to know where an A of any kind would be, but we just got rid of the goal. We got rid of the stop condition. We'd be able to then have a fully saturated graph. We'd know all the paths. And we'd be able to go through all the A's. So let me shift back to my planning mode. So I think the highest point at the start. Then stop when the goal is met. Would that work? We'd essentially get rid of the heuristic function, which might slow things down a lot, or it might not. Then go through and find all the A's, and iterate over them, find the path, and get the shortest one. Okay, I've already lost today, so I may as well just push ahead with this. Let's get us a timer going. Okay, so now let's change this. Okay, and we can say state. Okay, now this should still work, or not. the opposite path be that shouldn't make any difference. That shouldn't make any difference to anything. That shouldn't make any difference to anything. Why does it make a difference? If the goal is the start and the end, no. If the start point is the goal, and the end point is the start, that shouldn't make any difference, right? Do I do something else fancy with the goal? Do I set it anywhere? I don't ever use that. Oh gosh, let me wind this back. That's not right. Oh, actually, we can't do that because we have to, yes, I see. We have to flip this case. Flip that case. Yes, of course. Yes. Now, if we want to go in reverse, we've got to only allow walks that go only allow steps. This is the trick in this. Only allow steps that are either the same or one down or greater, but you can't do that anyway. Yeah. So or one down. So the neighbor's Z has to be greater than current Z minus one, right? No. Okay. So 26 can go to 25. It can't go to 24. It can go to 26 or 25. 25 can go to 20, 25 or 26, not 23. Can it go to 20? Can it go to Can it go to 26? If I had a 25, could it go to if it was the other way around and I had a Okay, so E can go to, so Z's the only thing that can come to E. So here we should only be getting left. So Z can go to Z. So Z is allowed to be, so this path is allowed to be equal. These are allowed to be equal, or they can be one less, or they can be any more, I think. But they can't be any more than, they must be greater than one less, right? So this rule should work, but it doesn't because I've not saved it. Come on. Well, that's pretty well, wasn't it? Yeah, okay. So that doesn't work either. Why doesn't that? Oh, maybe it does work. Yeah, so that works. The neighbors of cell X1, the neighbors of cell X1, Y1. Oh yeah, this is the problem. The neighbors of cell 0, 1. This needs to allow this one and this one. These should both be allowed, but they're currently not getting allowed. This one's not getting allowed. So should it be similar or equal to? No. Get further though. Okay, so now we get to cell 2, 1, which is this one, this one. Oh yeah, and that's because I've messed that one up. Fine. Length 31. Is that what it's supposed to be? 31. Yeah, that's right. Okay. So now if we plug in the real one, we should get the right number. 484. 484. Yeah, that's right. I don't know why that's upset at all. Now, if we, so we want to keep with the trial. Now, if we don't stop, we just keep going. How long does it take? Not so long. Okay, so we've now got the distance from every Z to every cell. And now we can go and change this. So we can iterate over target in what did I store it in? So state low points. Okay, let's try this. Is it finding all of them? There's 5 of them. 6 of them, rather. Okay, that's good. Now, we want to calculate the best path from the if we set the goal to be that's enough of that. We set the goal to be the low point when we reconstruct the path. When in the trial it's 29, which is what we expect because it's actually got to be the lowest. It's -1. 29. Okay, so the lowest is 29. This and then this was never even used. Just I already implemented the right thing, just through a bug. Okay, that's annoying. Fine. Fine. Let's just store them all before I let myself get messed up here. Should have a better way of doing this. In fact, it's fine. Okay, so that gets us 29. Now let's try it with the input. 0. Well, that's clearly not right. Yes, it is right. Probably not right. No, it's definitely. Why are some of these like, why are they 0? Doesn't make any sense. Is it because there aren't paths? Maybe it is. So we should end up at the goal, right? So, okay, let's try and filter these zeros out. Four, seven, eight. All right, let's try that. Well, pretty mushy, but did it in the time anyway. Whatever that is. Come on, focus. 12, 7. Oh, I forgot to stop it anyway. Anyway, so all right. Hmm, hmm, hmm. Starting to doubt the possibility of some of this. Okay. I will think about this. See you later.